Our goal is to calculate this limit numerically, algebraically, and graphically. So we're going to start with numerically using our graphing calculator. The nice thing we can do is we put this function in as a graph, and then we use the table feature. We do need to separate the numerator and denominator with a set of parentheses. Square root of x plus 1, close the parentheses for the square root of x plus 1, minus 1, close the parentheses for the numerator, divided by x. Okay? Now we could graph it, and we will look at the graph later, but we're not worried about that right now. What we're going to do is we're going to use the table. So let's zoom in a little here. And now we're going to go to second table. And I've already got my, well, I should show you the table set. You do need your independent on ask. Now remember, we want to see what happens as x gets sufficiently close to 0, but not actually be 0. So we're going to put in points that are close to 0. So 0.1 is very close to 0. 0.01 is very close to 0. 0.0001 is very close to 0. And look at what's happening with the y values. They seem to be getting closer to 0.5. Now we could put in 0, but we get an error, because if you remember what our original was, it divided by x. Well, that's dividing by 0, and so it's undefined. So as we come in from the right, into the right of 0, it looks like our y values are heading towards 0.5. Well, let's see if they go to the same place as we come in from the left. So we might do negative 0.1. Okay. Negative 0.01. So we're getting closer to 0. Negative 0.00. Let's get it real close. 0.1. Okay. The graphing calculator ran out of spaces, but look at how close to 1/2 we are. So what that's saying is, as x gets closer to 0, the y values are actually getting closer to 1/2. Now what we're going to want to do is confirm that algebraically and graphically. Now, whenever we have a radical in an expression like this, we have a nice technique we can use to help us solve this. And what we're going to do is we're going to multiply the top and the bottom by square root of x plus 1 over square root of x plus 1. The reason I'm doing this is twofold. Number one, this is just 1, so I'm not changing what I had. But the reason I'm doing this is because the numerator is going to FOIL. So I get, and I'll write out all the steps so you can see how this thing is going to simplify. First thing is I have square root of x plus 1 times square root of x plus 1. Here, I get a positive 1 times square root of x plus 1. Here, I get a negative 1 times square root of x plus 1. And lastly, I got negative 1 times 1 for a minus 1 at the end. What's really nice is those are going to cancel. And in the denominator, I have x, and I'm not going to worry about multiplying this out right now. We might do it later. Let's see what's going to happen. Times square root of x plus 1 plus 1. Well, those cancel, so that works out nice for us. The other thing, square root of x plus 1 times square root of x plus 1 is the square root of x plus 1 squared. So the square root and the square cancel. So that simplifies pretty nice for us too. So we have the limit as x goes to 0 of x plus 1, those canceled, minus 1, all over x times square root of x plus 1 plus 1. Well, those cancel. And I've got limit as x goes to 0 of x over x times square root of x plus 1, and then a plus 1 outside the square root. I can cancel an x out of top and bottom too. So now my problem is that I have limit as x goes to 0 of 1 over, remember we're just trying to find out the behavior of this thing near 0. X plus 1 plus 1. Here's what's really great about this. I can plug 0 in for x now because it's not going to make a 0 in my denominator. So if I plug that in, I get 1 over square root of 0 plus 1, or 1 over 1 plus 1, or 1/2. And there's our 0.5. So we've confirmed algebraically what we had numerically. Finally, we're just going to take a quick look at the graph. So here's a printout. Now your graphing calculator won't be able to draw it either. There's actually a vertical asymptote happening over here at -1. But that's not what we're worried about. We're worried about the behavior at 0. Well, notice what happens as we come in from the left, the y values approach 1/2. And as we come in from the right, the y values approach 1/2. So we can confirm graphically what we found numerically and algebraically, that as x approaches 0 for our function, the y values approach 1/2. And thus, that's our limit.